A mirror seems ordinary because you use it constantly, but it is one of the cleanest demonstrations of physics in daily life. It does not store pictures, and it does not generate images on its own. Instead, it redirects light in a highly organized way. Light leaves objects around you, reaches the mirror, bounces off according to strict geometric rules, and then enters your eyes. Your brain takes those incoming rays and interprets them as a coherent scene. That is why reflections feel immediate and alive. They are rebuilt continuously in real time. If you move, the reflected perspective changes instantly. If the light changes, the image changes too. This is important because it reframes what a reflection really is. You are not seeing a painted copy on glass. You are seeing a directional reconstruction of the world, created by controlled ray redirection. Once you understand that, a bathroom mirror, a car mirror, and a telescope mirror become members of the same family. They are all tools for controlling where light goes next. The core rule is simple but powerful. The angle of reflection equals the angle of incidence, measured against the normal line, which is perpendicular to the surface. This law is exact enough that engineers can rely on it for precision instruments. If a ray arrives at a certain angle, it leaves at the matching opposite angle. That consistency is what makes mirror-based vision trustworthy. When many rays from one object reflect in this orderly way, their spatial relationships are preserved well enough for your eye and brain to infer shape, orientation, and distance. Mirrors are therefore geometry machines. They transform incoming direction into outgoing direction with predictable symmetry. If the surface remains flat, image structure stays stable. If the surface is curved, the same law still applies at every point, but the local normals differ, so outgoing rays are redistributed in a controlled pattern. That produces magnification, compression, or distortion depending on design. The key idea is that mirrors are not magical image creators. They are direction-preserving interfaces, and the image appears because your visual system can decode that directional order. Not every shiny object works as a true mirror. The difference is specular versus diffuse reflection. In specular reflection, light leaves in organized directions, preserving image information. In diffuse reflection, microscopic roughness scatters light in many directions, which destroys the directional map. Matte white paint reflects plenty of light, but you cannot see your face in it because the incoming structure gets scrambled. A mirror surface must be smooth compared with light wavelengths so neighboring rays remain coherently ordered after reflection. That microscopic smoothness is the hidden requirement behind visible clarity. It also explains why mirror quality varies. Small surface imperfections reduce contrast, soften detail, and produce flare-like artifacts. This is why modern mirrors often use a thin reflective metal layer, such as silver or aluminum, supported by hard smooth glass. Glass provides stability and low roughness, while the metal provides high reflectivity. Together they create a practical balance of brightness, clarity, and durability. In short, reflection alone is not enough for imaging. A useful mirror needs reflection with preserved directional structure. People often say mirrors swap left and right, but that description is incomplete. A plane mirror actually inverts the axis perpendicular to its surface, meaning front and back are reversed relative to the mirror plane. Left and right feel swapped because you mentally compare the reflection to a person facing you, and that mental rotation changes your interpretation. Raise your right hand and your reflection appears to raise the hand on the opposite side of your view. It looks like a left-right switch, but geometrically it is a depth inversion with perspective consequences. This distinction matters because it shows mirror behavior is not arbitrary. It is a strict spatial transform. Vertical orientation remains upright, proportions remain consistent in an ideal plane mirror, and the apparent image position follows clear distance rules. Understanding this removes the mystery behind reverse text in mirrors and why mirrored choreography practice can still be physically accurate. The mirror is not confusing reality. It is applying a precise coordinate transform that your brain interprets through body-centered assumptions. A plane mirror gives the most familiar reflection because it preserves scale and shape without built-in magnification. The virtual image appears behind the mirror at the same distance the object is in front. If you stand 1 meter away, your image appears 1 meter behind the surface, creating a 2-meter apparent separation between you and your reflection. This equal distance rule explains why mirrors can make rooms feel larger. They add believable depth cues that extend perceived space. Interior design uses this effect intentionally to brighten and open tight environments. In practical settings like dance studios or grooming spaces, the geometric stability of plane mirrors provides reliable alignment feedback. But this reliability depends on surface flatness and quality. Slight warping can subtly bend straight lines and alter perceived proportions, especially near edges. So when we call plane mirrors undistorted, we mean relative to intended geometry and manufacturing tolerances. The broader point is that plane mirrors are powerful because they are optically conservative. They preserve visual relationships rather than aggressively reformatting them, making them ideal whenever accurate self-view or spatial judgment is needed. Curved mirrors are engineered trade-offs. A concave mirror curves inward and can converge reflected rays, which is why it can magnify nearby objects and reveal fine detail for shaving or makeup. Move farther away and behavior changes, scale shifts, and under certain positions the image can invert. A convex mirror curves outward and diverges reflected rays, which expands field of view while shrinking image size. That makes convex mirrors useful for traffic and security because they prioritize coverage over distance accuracy. The familiar warning that objects are closer than they appear exists because compressed images can mislead intuition about range. Neither mirror type is defective. Each is optimized for a different task. Concave designs favor detail and light gathering. Convex designs favor situational awareness across wide angles. In both cases, the law of reflection still holds locally, but changing surface normal across the curve redistributes outgoing directions nonlinearly. That nonlinear mapping is exactly what creates magnification, compression, and edge distortion. Curvature is therefore not just shape styling, it is information design in optical form. The history of mirrors is really the history of surface control. Natural reflections in still water were humanity's first mirrors, but water is unstable and angle-dependent. Early crafted mirrors used polished stone or metal, which worked but often dimmed, scratched, or tarnished. The modern breakthrough came from combining a highly reflective metal coating with a smooth, hard glass substrate. Silver and aluminum became common because they reflect visible light efficiently, while glass preserves a stable low-roughness base. This combination enabled consistent quality at scale, which transformed mirrors from luxury objects into everyday infrastructure. Better manufacturing meant clearer images, lower distortion, and repeatable performance across large batches. That repeatability is crucial not only for homes but for technical systems where alignment and measurement depend on optical consistency. The progress from hand-polished artifacts to industrial mirror production shows how small improvements in material processing can reshape daily life. Today's mirrors feel mundane precisely because centuries of engineering solved most obvious flaws, leaving us with an object that performs so reliably we forget how much craft is hidden inside it. Outside personal grooming, mirrors solve line-of-sight problems wherever direct vision fails. In vehicles, rear-view and side mirrors convert dangerous blind geometry into manageable information. In shops and corridors, convex safety mirrors reveal corners and aisle intersections. Dentists use small angled mirrors to inspect surfaces that direct view cannot reach. Periscopes use mirror pairs to let observers see above barriers without exposing themselves. The pattern is consistent. Mirrors relocate visual access without moving the observer to the viewed point. This passive rerouting of information improves reaction time and safety because it is continuous and immediate. Unlike snapshots, mirror feedback updates in real time as conditions change. That makes mirrors ideal in control loops where delayed awareness can cause errors or harm. Industrial operators, surgeons, and drivers all depend on this property. Even basic mirror placement becomes a design decision about what information should remain visible under constraints. Seen this way, mirrors are not decorative extras. They are low-power, high-reliability extensions of human perception that convert blocked spaces into actionable awareness. In advanced optics, mirrors become precision components rather than household surfaces. Telescopes use shaped mirrors to collect faint light from distant objects and direct it efficiently to sensors. This enables large apertures without the weight and chromatic issues that large lenses can introduce. Laser systems use mirrors to form resonant cavities where light bounces repeatedly, amplifies, and stabilizes into controlled beams. In metrology and industrial alignment, mirror assemblies steer beams along exact paths for measurement and calibration. Here, tiny errors matter. Minute angular misalignment can cause large downstream deviations, and small surface defects can degrade signal quality. Engineers must manage coating quality, substrate stability, mounting stress, contamination, and thermal expansion. Despite this complexity, the governing principle is still the same reflection law used by a bathroom mirror. What changes is tolerance. Consumer mirrors can be good enough. Scientific mirrors must be extraordinarily exact. That continuity is remarkable. One physical rule scales from daily routine to frontier instrumentation, with engineering effort determining how far performance can be pushed. The mirror concept extends beyond visible light because reflection is a wave phenomenon, not just a visual one. Acoustic mirrors and reflective surfaces can redirect sound, intentionally or accidentally. In rooms, untreated walls and ceilings may create echoes that reduce speech clarity, while carefully designed acoustic geometry can improve intelligibility and recording quality. In marine and atmospheric applications, controlled reflection supports mapping and detection methods related to sonar behavior. At even more specialized levels, researchers use systems that reflect matter waves, enabling techniques such as atomic interferometry and atomic holography. The media differ, but the logic stays familiar: preserve or shape wave direction to extract useful information. Thinking this way broadens what a mirror means. It is not merely glass with metal backing. It is any boundary engineered to reflect waves with enough structure for a purpose. That purpose might be seeing your face, detecting terrain, stabilizing a laser, or probing quantum scale effects. The mirror idea therefore sits inside a larger language of wave control that supports modern sensing, communication, and imaging technologies. Mirrors also carry cultural weight that goes far beyond optics. Superstitions like 7 years of bad luck after breaking a mirror persist because mirrors are psychologically intimate. They return your own image instantly, so damage can feel symbolically personal even when the event is physically trivial. Across art and architecture, mirrors have represented vanity, truth, deception, status, and self-examination. They can enlarge spaces, amplify light, and create dramatic visual narratives in interiors. This cultural layer does not change the physics, but it changes how mirrors are used and interpreted. A lab mirror is judged by surface figure and coating durability. A home mirror is judged by those factors plus emotional effect, aesthetics, and social function. Understanding both dimensions helps explain why mirrors remain central objects in daily life, technically straightforward, but deeply tied to identity and environment. They are among the few technologies that are simultaneously measurement tools, design elements, and psychological interfaces. That combination gives mirrors unusual staying power across eras and contexts. If you reduce everything to one line, a mirror is a precision surface that redirects waves predictably enough to create usable images or measurements. From that definition, all major uses connect: personal grooming, safer driving, wider situational awareness, architectural depth effects, telescopes, lasers, and scientific sensing. What makes mirrors powerful is not complexity but reliability. They perform a strict directional operation again and again with minimal energy and no computation. Your brain does the reconstruction, and because optical rules are consistent, the result feels natural. The next time you look into a mirror, it is worth noticing that you are watching a live physical process, light leaving objects, bouncing with geometric fidelity, and being interpreted into space by perception. That process is ordinary only because it is constant. In reality, it is one of the clearest windows into how the physical world becomes visual experience. Mirrors do not just show appearances. They reveal the mechanics of seeing itself. If you found this helpful, please like this video and subscribe for more explainers.